All right, today we're pulling back the curtain on something super important. What does it really take to train a machine learning model for production? We're going to dive deep into the ShopSmart case study and take apart a real-world training script line by line to see how the pros get it done.
You know, if you've ever messed around in a Jupyter notebook, the code on the left is your best friend, model.fit. It's great, it's perfect for exploring. But to actually launch a model and have it work reliably out in the wild, you need the kind of discipline and structure you see on the right, a proper production script. The gap between these two, it's huge, and today we're going to build the bridge.
And why bother with all that extra discipline? Well, how about this for a reason? This is the actual return on investment from ShopSmart's MLOS system. A mind-blowing number like that doesn't just happen by magic. It's the direct result of serious engineering rigor that's baked into every single line of their training pipeline. And that's exactly what we're going to unpack.
So here's our game plan. We're going to follow the logic of that train-model.py script. We'll kick things off by looking at what makes production so different from a notebook. Then we'll get into the nitty-gritty, splitting data the right way, training a model that's actually robust, tracking our experiments with MLflow, versioning the final model with DVC, and then we'll wrap it all up into a blueprint you can use.
Okay, let's dive right in. The very first thing a production script does, right after it loads the data, is get it ready for training. And for ShopSmart, this means immediately facing one of the most classic challenges in all of machine learning, class imbalance. And here's the problem in a nutshell. Look at this. Only 15% of ShopSmart's customers are in that churned category. Now, if you just split your data randomly, you could easily end up with a test set that has almost no churners in it. Your model could just guess not churned every single time and score an 85% accuracy, which of course makes it completely useless in the real world.
So, how do we fix this? What's the professional move? It's a technique called stratified splitting. It's actually a pretty simple idea. Instead of a totally random split, it makes sure that the 85-15 ratio of customers is perfectly maintained in both the training data and the test data. This is how you guarantee your model is being tested on a realistic slice of the world.
And boom, here's the result. It's beautiful, right? After doing a stratified 80-20 split, our final test set, all 20,000 customers, perfectly mirrors that original 15% churn rate. This right here is the absolute non-negotiable first step to building a model you can actually trust.
All right, our data is split the right way. Now for the main event, actually training the model. And look, the goal here isn't just to get the highest possible score on our training data. The real goal is to build a model that can generalize, that works well on new customers it's never seen before. So, when you peek inside that train-model.py script, you won't just see a basic model.fit. No way, you'll see specific parameters like these, all designed to fight overfitting. Max depth stops the decision trees from getting ridiculously complex. Subsample and call sample inject a bit of randomness, forcing each tree to train on a slightly different slice of the data and features. And early stopping? Oh, this one's a lifesaver. It just stops the training process if the model isn't getting any better, which prevents it from just memorizing the answers.
I absolutely love this analogy because it just hits the nail on the head. Overfitting is basically just memorizing the answers to a practice test. Sure, you'll get a perfect score, but have you actually learned anything? Nope. Generalization, on the other hand, is about really mastering the material so you can crush the final exam, which, for our model, is predicting churn on brand new customers. These parameters are how we force our model to learn, not just memorize.
Okay, this next part is, for me, where things get really interesting. A production pipeline has to make sure that every single training run is completely accounted for. I mean, we've trained a model, but how do we prove we can get this exact same result again 6 months from now?
Seriously, this is the kind of question that should keep data science teams up at night. A regulator might come knocking, or a new teammate might need to figure out why performance suddenly dropped. If you don't have a system of record for your experiments, you're flying blind. This is the exact problem that experiment tracking was born to solve.
And the solution in the ShopSmart script is, well, it's brilliantly simple. It's just one line of code, MLflow.autolog. That's it. This one command turns MLflow into this incredible digital lab notebook. It automatically grabs everything, the exact hyperparameters, all the performance metrics, the model file itself, and even the precise versions of every library you used. It's a guarantee for 100% reproducibility.
So, our experiment is logged,
The final critical step in the training script is to properly save and version the model file itself. And this isn't just about sticking a file somewhere. It's about creating a secure, auditable, production-grade asset that the business can truly depend on.
And let's remember what's at stake here. This one model is saving the company almost $4 million a year. You can't just have a file called model.pkl sitting on some developer's laptop. It's too valuable. You need a rock-solid version-controlled system to manage it. And that brings us to DVC, or Data Version Control.
Now, a question I hear all the time is, wait, if I'm using MLflow, why on earth do I also need DVC? And this table makes it super clear. They're not competitors. They're teammates. They're complementary. MLflow is your experiment lab. It's got a great UI for comparing runs and a registry for promoting models. DVC is your version control system. It plugs right into Git to create this unbreakable link between your code, your data, and your actual model files.
So what does this actually look like? It's way simpler than you might think. It's basically a 4-step dance on the command line. After you save the model, you run dvc add to tell DVC, hey, start tracking this file. Then you git commit that tiny little pointer file, which creates a permanent record. And finally, DVC push securely sends the big model file up to the cloud, like Azure Blob Storage. It's literally Git, but for your data and models.
So let's just take a step back and think about what we've done. The crucial point here is that by just following the logic inside this one Python script, we've uncovered a complete blueprint for taking a machine learning idea and turning it into a reliable, reproducible, and truly production-ready asset.
So let's recap the 4 pillars of this blueprint. 1. You have to start with a stratified data split, especially if you have class imbalance. 2. You train for generalization, not memorization, using smart parameters like early stopping. 3. Use a tool like MLflow to automatically log every single detail, so your work is always reproducible. And 4. You use DVC to create an unbreakable, auditable history of your models, linking them forever to the code that created them.
So we've done it. We've built a solid foundation. We have a robust, versioned, and totally reproducible model artifact. But that's really just the end of the beginning, isn't it? The next big question is, okay, what does it take to deploy this thing, to monitor it in the real world, and automate this whole process so it runs by itself? Well, that's what we'll dig into next time. Thanks for joining me.